Hello, this is Dr. Moore, and this video is the first in a two-part series that will review geology concepts for AP Environmental Science students. The geology concepts in the AP Environmental Science curriculum always stood out to me because they kind of felt less connected to the rest of the course. So I'd like to start by explaining how geology fits into the other concepts within AP Environmental Science. First, I would argue that geology literally underlies all other APES concepts since everything we talk about in AP Environmental Science sits on the surface of our rocky planet. But here are some more specific ways geology relates to the rest of AP Environmental Science. First, geology shapes mountains, and mountains influence rainfall. Mountains dictate the flow of surface water on land. Geological processes are critical in the cycles of elements such as carbon and phosphorus. Geology explains the global distribution of mineral resources such as coal, uranium, copper, gold, and aluminum. And geological hazards such as volcanoes and earthquakes create risks for human life, but these risks can be mitigated through planning and engineering. A magnitude 7.0 quake killed 230,000 people in Haiti in 2010, while a much more powerful earthquake in Japan the following year killed only 1,600 people. So that's why we need to study geology and AP Environmental Science. Perhaps the first thing you should know about the Earth beneath our feet is that it has layers. Now, precisely what those layers are depends on what you are interested in. Folks who are interested in breaking up the Earth according to its chemical composition see three layers: the crust, the mantle, and the core. Those who are interested in the physical properties of each layer see five layers: the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core. The lithosphere is the rigid outer shell of the Earth on which we live. The asthenosphere is the semi-liquid, gooey layer upon which the lithosphere floats. There's the mesosphere, and you don't really need to know that much about the mesosphere. The outer core is the only truly liquid layer of the Earth. It is made from molten nickel and iron. And the inner core is under so much pressure that it's solid despite being incredibly hot. Like the outer core, the inner core is made from a mixture of iron and nickel. I'd like to point out that no one has ever directly observed the interior of the Earth. The radius of the Earth is 6,371 kilometers, and the deepest hole ever dug by humans, the aptly named Kola Super Deep Borehole, reached only 12.2 kilometers into the Earth. Instead, scientists have constructed this model of what the Earth's interior must look like by studying refraction patterns of earthquake waves. Earthquakes and volcanoes also reveal to us the boundaries between tectonic plates. This map shows us that volcanoes and earthquakes are not randomly scattered across the surface of the Earth, but instead follow sinuous paths. It turns out these paths trace the edges of the Earth's tectonic plates. The lithosphere of the Earth is not continuous, but broken into fragments that float on the asthenosphere below. We call each one of these fragments a tectonic plate, and at their borders, the tectonic plates interact. The exact nature of the interaction depends on the plate's direction of movement and also their composition. At a convergent boundary, plates move toward each other. At a divergent boundary, they move apart. And at a transform boundary, the plates slide past each other. As far as composition, there are two main types of crust. There's oceanic crust, which tends to be thinner. It is made of a rock called basalt. Think of the black rock that is formed by the cooling of lava in Hawaii's volcanoes. And most importantly for us, it is more dense than continental crust, which by contrast is thicker. It tends to be made of granite. Think of that speckly rock that is popular for tombstones and countertops. And again, most importantly for us, it is less dense than oceanic crust. For our purposes, the most important difference is that oceanic crust is denser than continental crust, because this is going to explain the behavior of different plates when they meet at a convergent boundary. The denser oceanic crust will sink beneath the less dense continental crust. We call this process subduction, and we'll take a closer look at it in our second video. Right now, I'd like to talk about the cause of plate tectonics. Why are these plates moving around anyhow? Well, the science isn't completely resolved on this question, but it looks like mantle convection currents are at least part of the answer. The core of the Earth is very hot, and it heats the rock in the mantle. As the rock warms, it becomes less dense and it rises. Once at the top, it is displaced by the rising warm rock behind it and pushed to either side. As it moves to the sides, it drags the lithosphere with it, moving lithospheric plates apart from each other. Eventually, the mantle rock cools, sinks down to the bottom where it is heated again, and the cycle continues. Note that the movement of rock in the mantle is the same as the movement of water in a pot on a stove, and the movement of air in the Hadley cell. But why is the interior of the Earth hot? The number one source of Earth's internal heat is the radioactive decay of radioactive elements such as uranium and potassium. This is the same energy used in a nuclear reactor. When the nucleus of a radioactive atom splits, it releases some energy as heat. This concludes my first video on geology for AP Environmental Science. In my next video, I'll talk about the different tectonic plate boundaries and their associated geological features, and I'll also talk to you about volcanic hotspots.